So good morning to you all. A warm welcome to the second PFPNet Tunnels Committee webinar on tunnel fire safety. Today's guest is Mrs. Tineke Wiersma of RWS in the Netherlands. And Tineke will provide an introduction as to how tunnel safety, fire safety in tunnels is incorporated in the Dutch tunnel safety regulations and risk methodology in particular. Tineke is a senior consultant in the Dutch Ministry of Transport, and she participates in several design and construction projects for new tunnels as well as retrofitting tunnels in the Netherlands. She's joined RWS Rijkswaterstaat some 14 years ago now, after a career in the Dutch research organization TNO. Where she was a project leader, a consultant, and researcher in the Department of Industrial and External Safety, dealing amongst others with external safety, risk analyses, and obviously also tunnel safety. She graduated in 1989 in applied mathematics and had a postdoc position at Nijmegen University on the topic of system dynamic modeling of dental care systems in the Netherlands, a totally different topic, of course. Before we give the floor to Tineke, I'll hand over to John Dunk, who will introduce PFPNet more broadly. And I guess you all know the drills of webinars and seminars, so please would you mute yourselves and switch off your videos such that the bandwidth of the video connection stays good. There is an opportunity for questions. Please provide them in the chat box so we can moderate after the seminar, and we will take some questions live. Where we run out of time, we will deal with these questions separately. So please leave then also an email address so that we can answer to you directly. So without further ado, I'll give the floor to John, who will hand over then to Tineke for the presentation. Thank you, and enjoy the webinar, of course.
Thank you, Kees. Well, good morning. Welcome to this PFPNet presentation. For those of you who don't know PFPNet, firstly, let me welcome you to this PFPNet event, along with our other participants, and perhaps I might briefly explain what PFPNet is about. PFPNet is a not-for-profit industry organization which was formed to improve knowledge and understanding and standards in hydrocarbon passive fire protection, primarily for the oil and gas industry, but also for other industries with high-risk environments where fire can be seen as a primary risk, and in tunnels in our case today. Our membership is global and comprises owners and operators in the industry, as well as engineers, contractors, regulators, and others who are involved in fire protection. We are funded totally by the subscriptions from our members, managed by a steering committee whose role it is to ensure that PFPNet is run to the benefit of its members and utilizes our subscriptions funds wisely in pursuit of our objectives. Our activities in fire protection are varied, but we've always used the principle of going to our members to ask what are their key issues and what do they want to see attended to by PFPNet, using the expertise we have brought together by having a diverse membership with experts in all areas of passive fire protection. So over the past few years, we've been able to tackle many subjects successfully, some of which have been in the industry unaddressed for many years, and others, such as the very real potential for the use of hydrogen in mass transport, being new challenges for the industry to evaluate. And that's one of the areas we're currently working on. If you're not already a member of PFPNet, could I encourage you to go to www.pfpnet.com to learn more about our activities and hopefully become a member. So that's briefly what PFPNet is about. So I think it's now time to hand over to Tineke to provide you with the presentation, which we all look forward to this morning. And as Kees explained, there will be time for questions later through the chat function. So Tineke, over to you.
Okay, thank you. Then I have to share my screen. And I think you all see my screen now.
Perfect, thank you.
Okay. Well, as Kees already mentioned, I work for RWS in the Netherlands. That's the main road authority in the Netherlands. And we also well, have some tunnels in our network, and we have the regulations on tunnel safety developed. Next slide, yes. Well, in my presentation, I will first explain a bit on how tunnel safety regulation is implemented in our legislation, and the EU directive is also implemented in our national legislation. Then I will go into the risk analysis methods. Two methods are prescribed in our regulation. And then I will go into more detail into the quantitative risk analysis method. And well, since this is for PFPNet, I put also a short introduction on how we have fire protective measures in the model and how we can see if it influences the risks. And well, at the end, maybe there will be some time for questions. I can try to see the chat. No, it's not there. Okay. Then first to the tunnel legislation in the Netherlands. As you may know, we have this EU directive of 2004 on the minimum safety requirements for tunnels in the Trans-European road network. This EU directive of 2004 was implemented in the Dutch legislation in 2006. And well, actually it's a bit more strict than even the EU directive. So we apply it to all our tunnels, not only the tunnels in the Trans-European road network. And it's mandatory for all tunnels longer than 250 meters. Well, since we have this legislation, we still had some discussions on tunnel safety, and that was one of the reasons that in 2013 our Tunnel Safety Act was updated. Well, it's updated regularly, but a major change was done in 2013. And one of the major changes that was that we also prescribed a standardized set of equipment that is mandatory for all new state-owned road tunnels. And well, it's not mandatory for city tunnels, but they usually also apply the same standard. And we also prescribed the standardized QRA method in our legislation with a legal safety criteria which has to be met by all road tunnels. And well, in our 2006 legislation, we also had the deterministic scenario analysis, which was already there, but we had a lot of discussion on this scenario analysis. So we changed in the 2013 Act that the position of this scenario analysis should be focused on the preparation on emergency response, and not on discussions on which equipment to be used, because that is all prescribed now in this standardized set of safety equipment. So we have two risk analysis methods. These probabilistic and a deterministic approach. They are both prescribed in the law, and the quantitative risk analysis is used to check if the tunnel meets the legal safety criteria. I will show you that later on. But we can also use it if we have to investigate the effectiveness of more risk-reducing measures. And second, the scenario analysis is now used to have a communication with the emergency response services, and we apply this with the emergency response organizations in the vicinity of the tunnel to give them insight in the tunnel system and to investigate how emergency response should be handled in the case of an accident. Well, we in earlier years, since 2006 and up until 2012, when we started with this new tunnel safety law, we also applied it on during the design stage to determine which equipment to apply. But since we didn't have a legal risk criteria, it led to a lot of discussion on which scenarios to use and when it was safe enough. But this scenario analysis we still apply, and we also have a guideline on how to perform this analysis. So we follow 6 steps. First, we select the scenario analysis team, which is mostly by a risk analysis, but also representatives from all emergency response services and the tunnel operator. Then we determine which safety targets we want to examine. The third step is to describe the tunnel system, and in the fourth step we select the scenarios that we want to examine. And then the major step is the analysis of the scenario. So then we walk through the events during a scenario and what the response of the different organizations involved will be. And then at the end, we evaluate if we have all possible measures taken, and if there are what recommendations we should follow in the preparation of the emergency response. As I already mentioned, we had a lot of discussion on the acceptability of the risk and additional safety measures in the stage where we also applied it during the design stage. So we changed that, since we didn't have a risk criteria to compare it with, we changed that in the updated tunnel safety law. And since we already prescribed all the safety measures in this new tunnel safety law, it was not longer useful to have this discussion during the scenario analysis. And in the new scenario analysis, the focus is entirely on the preparation of emergency response procedures. So that's how we apply it currently in our new and refurbished tunnels. Well, and the quantitative risk analysis, as contrary to the scenario analysis, it analyzes a much larger set of scenarios, and we also take into account the probability of these scenarios. And in our quantitative risk analysis, we also have to quantify the consequences. We mainly use it to compare alternatives. We also apply it to see the effect of safety measures. But the main use now is to compare it with our risk criteria, which is also in the safety law now. So if you see this graph here, and I think you can see my pointer on the screen, this is what we calculate. Check the next slide. In this quantitative risk analysis method, we calculate the risk, and we quantify it and display it in an FN curve, where we have the number of fatalities compared to the accident frequency, which is expressed in per kilometer tunnel per year. And this risk criteria is also prescribed in our tunnel safety law. And so after the calculation, which we have to do for every tunnel tube separately, it has to show that this risk line has to stay beneath this risk criterion. The model itself is actually a very large event tree describing all possible events and variations on the event. And well, the risk is a combination of the number of casualties for each event and the probability on that event. Well, we had this risk method also earlier in 2006, but then when leading up to this updated tunnel safety regulation in 2012, we developed a dedicated risk model for quantitative risk assessment for road tunnels. Well, this development took several years, but when it was more or less finished in 2011, we also did a consequence analysis and acceptance tests for all our tunnels to see which tunnels would meet the criteria and which not, and how it compared to other risk models before we implemented it in the tunnel safety law. We also made a comparison with the PIARC model of DG Curam. Well, they are not really completely comparable, but well, it gives some insight in how they quantify these scenarios and which scenarios they had in the model and what we did. I think the RWS model has some more details on the fire consequences and the influence on equipment. And well, we use it for a different purpose than the DG Curam model. We don't use it for the comparison of routes, and we don't include the external safety and on the different routes and the route outside the tunnel. So there's some differences, but well, we did this exercise to improve, to see what our model was fit for purpose. And well, we also had it reviewed by several research institutes in the Netherlands. So we now apply it for every tunnel during the design process of the tunnel to prove that our tunnel is safe enough, that the tunnel that will be built is safe enough. And once the tunnel is ready and in use, the QRA has to be kept updated during the lifetime of the tunnel to prove that the tunnel still meets the safety criteria. And well, the risk is highly influenced by the traffic intensity and the use that is made by, for instance, dangerous goods. So it can change over time. So that's why we have to keep this QRA updated. And well, if you don't meet this risk criteria, then we have to take alternative measures to reduce the risk. Well, in the model, the main, I hope you still see my screen, but I can see nothing. So I think, so still okay?
Yeah, screen is still good.
Okay. Then the main principles of the model. Well, of course, it's model, so we have to simplify reality a bit. So wherever it's necessary, we applied some simplifications. The quantification of the risk is mainly on lethality, so we don't calculate injuries or material damage. Well, we had some experiments in extending the model also to a material damage model, but well, since our risk criteria is mainly focused on the lethality now, and all uh, um, risk material damage measures on diminishing material damage are prescribed in our law. Also, there's not much demand for a model on material damage, so we don't use that now anymore. And our model calculates the consequences on lethality in the first hour after the accident. So we assume that everybody who survives the first hour and is able to rescue itself from the tunnel is safe. Well, maybe some people will have serious injuries and die later. That's not included in the model, but and we also do not include the contribution of the emergency services who may be able to rescue some people later on from the tunnel. So we do some conservative estimates on the number of casualties. And well, we try to simplify if possible when it has little influence on the risk, but when it's more complex or when risk reducing measures have more influence on the events, it's made more complicated. So for instance, fire is yeah modeled much more complicated than an explosion, for instance. I will explain a bit on the consequence modeling in the next slides. Well, this is the full event tree. It's a bit large, so, and I'm afraid you cannot read everything, and it's in Dutch, but I will try to explain it step by step. Well, first of all, we start with the type of incidents with because it can influence the fire growth and the number of cars involved. So we start with, is it a collision or is it a breakdown? And then the time of the day is important because in the evening or night there will be not many cars involved, but during peak hours the tunnel will be filled with cars when there's an accident. So that is incorporated in the model to quantify the consequences. Well, the one important thing is also the number of traffic jams, especially traffic jams downstream the accident. So if we have a traffic jam already in the tunnel and one or more cars hit the tail of the traffic jam, then it will influence all people in the tunnel. And since we have ventilation, longitudinal ventilation in almost all our tunnels, then the heat and the smoke will be over this downstream traffic jam. So that will have major consequences in the model also. So the location in the tunnel, we have different in the model. We have 3 different locations where we calculate consequences. The slope of the tunnel also influences how the spill of dangerous goods is distributed. So that's why we have 3 places in the model. Well, then we have a lot of detection equipment in most of our tunnels, and early detection can also help to influence the consequences. If the operator, which we also have in all our tunnels, detects the accident very early, it can start the tunnel equipment immediately, so it can start the ventilation and the evacuation, which will have a positive effect on the consequences. So we have fire detection, but we also have speed detection in most of our tunnels, so it's also in our model. Well, the type of cars that definitely has some influence on the fire size. We consider several fire sizes ranging from 5 megawatts to 200 megawatts. And well, a major influence is also the bulk transport of the dangerous goods, which is allowed in most of our tunnels. So we have this distinction between flammable liquids, flammable gases, and toxic liquids and gases. Well, toxic gases and flammable gases are not allowed in all tunnels. They are allowed in our land tunnels, but they are mostly not allowed in our underwater tunnels because we think the risk of explosion and the consequences for the tunnel construction are too severe. And then we have different equipment in the tunnel and in the model that can influence the consequences, like ventilation, escape doors, and the closure of the tunnel immediately after the detection of an accident. Well, and in some cases, a fire or an accident can also block the escape doors, which is also included in the model. So this is a lot of branches in the event tree, and well, depending on if you have all dangerous goods in it and all equipment, that can mean that we have to calculate about 500,000 scenarios. So that's well, that does the model, and well, to do the calculations, you have to put some input into the model. So we have to give the data on the geometry, the length, for instance, of the tunnel and the width. All safety features in the tunnel, like ventilation, operation, the operator, the loudspeakers, the distance between escape doors, and well, the detection possibilities. Other inputs are the number of occupants, the traffic intensity in the different periods of the day, the traffic composition, and the downstream traffic jams have to be also estimated and put into model. And we start with the incident frequencies. It's the major, so the frequency of collision or breakdown are input parameters. So that's not calculated by the model itself. We do have a smaller model, which is made in a spreadsheet to make some estimates if you don't have any data on your tunnel for this incident frequency. You can use this model separately to make an estimate for the incident frequencies and then implement it in the QRA model. Well, the model calculates the expected value of the risk. So it's the number of casualties per year. And you can it also calculates the personal risk, which is the risk of an it's expressed per kilometer traffic. And the main use is the calculation of the societal risk, which is expressed in an FN curve. And we compare our risk with the risk criteria. This is here in this graph. And well, as I mentioned earlier, when after calculation, every tunnel tube has to meet this risk criteria, so it has to stay below this this line. Well, we need a lot of data and formulas to fill this model and to make these quantifications. So for the accident and fire frequencies, we did some additional research, and well, we used data and expert opinions to make these estimates. Well, we did some research on the frequency of fires in trucks. Well, we are more interested in trucks than passenger cars because the fire size of trucks is more severe and has a higher risk on casualties. So we did some research on that, on data in the Netherlands, but also data from European countries to make an estimate for this this fire risk. This is the result that is that fire risk for heavy fires for trucks larger than 25 megawatts is about 1.5 times 10 to the minus 10 per vehicle kilometer. So that's an input that you can put into the model. And for car accident frequencies, we use a lot of statistical data for all existing tunnels. And well, for our existing tunnels, we can use the data for the tunnel, but for new tunnels, we also use this statistical data for the old tunnels, but then we put this data into a separate model and make estimates of the influence of the geometry of the new tunnel and the road design, traffic intensity. And with this estimate, we can give an estimate of the accident frequency for the new tunnel, for the tunnel to be built. So that's the probability side of the model. Then the most work is done by developing the model on the consequence modeling. We also used models that were already available for external safety, but we had to make some more research for the consequences in the tunnels. Well, for dangerous goods, we have 4 categories: the liquefied, flammable liquids, the flammable gases, and the toxic and the liquids and gases. For each category, we have 3 different release sizes, and the results and consequences of the calculations are expressed in the effect areas in the tunnel. So for each scenario, we calculated the length of the consequence area, and then it is transposed into the number of cars in this area, and then the number of casualties is calculated. For fires, it was more complicated. We did several CFD calculations for different fire sizes for a sort of standardized tunnel, and for fires with or without this longitudinal ventilation working. And these standardized fires are incorporated into the model. Well, I think that's in the next slide. A bit more on the CFD calculations. The calculation of the fatalities is a comparison between the maximum dose that people have on smoke and the maximum dose on smoke and heat leads to the available time to escape, and the walking speed and the distance between escape doors gives you the required time to escape. Well, and if you compare these two, if the required time is more than the available time, that means that you will not reach the escape door in time, which will lead to fatalities. Well, all the formulas and on how it's all calculated are in our background document, which is also publicly available, but it's all in Dutch. So the CFD calculations, we applied them for a standard tunnel with a width of about 13 meters and a height of about 5 meters, a rectangular tunnel. And we did calculations for several fires, and to see how they the configuration of the tunnel influences the results, we did some sensitivity analysis as well. And well, if you have this CFD calculations here, you see some of the nice pictures that a CFD calculation can give. We have this here. You see one of the graphs resulting from this. The blue one is the graph from a CFD calculation, and we linearized this result with a conservative estimate. So we followed this this line and made a graph which symbolizes the results of the CFD calculation. In this example, it's the CO concentration at a certain location in the tunnel at a 200 megawatt fire with ventilation. So we made graphs like this for all CFD results and put them as functions into the model, and the functions are then used to calculate the maximum dose in order to survive the consequences of the fire. So that's a bit most for the consequence modeling so far. Well, what do we do with the passive fire protection in the model? If you open the model, you will get how do you call it? You get several sheets where you have to put in all the parameters which are used to calculate the risk. And one of the sheets is about all the equipment in the tunnel. And there you can also fill in if it has pacifier protection. So we put this in the model, this parameter, but since we decided not to develop the material damage calculations any further for now, we are not really using this parameter, so it doesn't actually do anything to calculate the risks. When we developed the model, we also did CFD calculations with or without pacifier protections. But the consequences on the number of casualties were not really significant. So we decided not to take this parameter into account when calculating the number of casualties. So for this public, it may be a bit disappointing that we did have this parameter on pacifier protection in the model, but it's not really used. But we did use all the event tree which we developed for the QRA model, and the data on the statistics. We do use them from time to time to do separate cost benefits analysis on how to apply pacifier protection or not in the tunnels. So we did that a few times when we had some discussion on replacing pacifier protection in some of our older tunnels where there were some problems with the pacifier protections, and can we take it out or do we have to repair it? That question was developed. We developed a separate cost benefit analysis using all the event trees and data in this QRA model to see that it would be cost effective to repair the pacifier protective. Well, we also had a lot of discussion on active fire protection and whether or not to apply it in our tunnels and to include it in our standard set of safety measures. It's not a standard parameter in our model. It's not that you can put in the parameter we have or we don't have active fire protection because, well, we didn't put it in the model because at the time that we developed the model, we didn't have, well, we only had one tunnel with active fire protection and all the others didn't. So, but you can do some calculations to see the effectiveness of this system by making some changes in the probability of extinguishing the fire. In the model, we have besides the input values, we also have a lot of default values which are used to calculate the number of casualties, and one of the default values is the probability of extinguishing the fire and the probability on fire growth. And for if you want to apply active fire protection in the model, you have to make some changes in these default values. For here you see that we estimate that the probability of extinguishing a passenger car is 0.25. When you have no active fire protection, this is the probability of extinguishing the fire by using the fire hoses and that are in the tunnel. So if you have active fire protection, you could increase this extinguishing probability and then see what the results of active fire protection will be, like water mist or sprinklers. Well, we use the model since 2012 for all our state-owned tunnels, and for all these tunnels we made QRAs and reports and checked if the tunnel meets the risk criterion. Well, there was one tunnel that did not meet the risk criteria. That was one of our older tunnels, and we had to also had plans for refurbishing this tunnel. So we since then we also already refurbished that tunnel. So now it's also compliant with the risk criteria. And then later on, it is also applied for all the other tunnels in the Netherlands, which are mainly in the cities. And they had some more time to comply to the legislation. They had to meet the risk criteria in 2019. Well, for some of those older city tunnels, some adjustments had to be made also to meet the risk criteria. So they had to apply, they had to refurbish the tunnel. And the model is also used in Flanders, in Belgium. Well, and it's available also in other countries, but that I cannot see if they apply it or not. And well, it's a standardized model for our typical Dutch tunnels, but for two specific tunnels with a very specific configuration, and one tunnel with which had a very specific traffic use. It was only for buses, and they had several procedures. We made a dedicated version of this standardized QRA model. So most part of the model was made the same, but some extra events were included to have a good calculation of their risk. Well, I think our methodology is very transparent because the model and all the formulas that we use are completely described in the background documents. And although some of the formulas are quite complicated, the model itself is very user-friendly. You only have to apply the data, and then the calculation is very easy. Well, for now, the model is still used, but at the moment we are doing some extended research on new energy carriers because we want to know if we have to extend the model to the new energy carriers like hydrogen cars and buses. So I hope by the end of next year we know if and how we have to extend the model for buses and trucks with hydrogen tanks. Well, since 2006 we didn't have an officially new of 2012. We still use the same version of the model, although we had some minor bugs and some corrections. It's not it wasn't really important to have a new and updated version, but well, we will give a new updated version as well in a few years when we also know how to implement hydrogen. Well, and I think I already mentioned that we did some research on extending the model with material damage, but we haven't implemented it yet because we have no real need for expanding the model on that part, and we use the knowledge we have from that research for separate cost benefits analysis, but we didn't implement that in the model itself. So I think, oh, that was a bit too fast. I think we are almost at the end of the slides. I think I ended here. Then yes, so finally, last sheet before the questions. Well, we did we apply in the Netherlands a combination of this quantitative risk analysis with the prescriptive approach for all the safety equipment in our tunnel. And this combination is for us shows us a very good basis for decision making. Well, since the model is freely available since 2012 and described in the tunnel safety law, it's also very generally accepted method now. And since it is standardized, we hardly have any discussion on the methodology anymore. So now we can focus on the tunnel itself and on how to apply all this technical equipment and on the organizational procedures to be taken. Well, if you are interested in the model itself, it's freely available and you can order it with me or my organization. But well, we made it for our own use, so it's only in Dutch. And well, the model itself doesn't have that much text, so I think it's not very difficult to use if you don't speak Dutch. But if you want to know all the background, well, all the background material is also in Dutch. So that was the end of my presentation, and I think we still have a little time for questions.
Yes, thank you, Tineke. All clear. Thanks a lot for the comprehensive overview. I think you can talk for a couple of days on this topic. You're the top-notch expert on this model and how it was developed essentially from scratch. From I think it was back in the day, it was an Excel first development.
Yes, that's
with your
correct.
former colleague Jelle Hoeksma, and this is now a rather advanced, I would say, model. Yeah, so there are some questions I think in the chat, at least one from Sabu Thomas, and he asks after the EV cars, or probably this extends to any other car then or vehicles with conventional engines, but electrical propelled vehicles or any other hydrogen, perhaps fueled cars. Have they been of influence in the developments of your model? And how are you taking this into account for future releases of your model?
Well, we did some research, I think several years ago. We started it because then we already saw that there were some developments on new energy carriers like electrical vehicles. And well, we also had a fire out on the open network with a natural gas bus, which had a very nice jet fire and a very nice film on internet. So then we had a lot of questions on should you not extend your model with new energy carriers. So we did some research. We asked TNO to do that research a few years ago to see if electrical cars and natural gas and hydrogen gas would have serious consequences for the risk in a tunnel, and or that we could also use the model by changing some of the parameters. So we, as a result of this research, we were not very concerned about electrical cars and buses, because, well, they do have different fire fire consequences, but mainly they are longer, the fires, but not more severe. So we don't expect that it will have more casualties, but, well, it's a different way of extinguishing the fire, but that's not the focus of the model. So we do not have any plans to extend the model with electrical cars or electrical buses, but we are more concerned about hydrogen buses and trucks, and we are still doing some research on that to if we have how to model that into the model, and then we will implement it and see if it has significant consequences on the risk. But, well, as soon as we finished that, we will see if we can extend the model with that, because mainly the possibility of explosion should be investigated in the model to see if it has significant consequences on the risk.
Okay, thank you. One final question, perhaps looking at the time. And those of you who may have other questions, perhaps you can tune in for the second session of this webinar, which will be broadcast in 4.5 hours, I think, from now. So you might sleep over it or have a coffee over it and think of other more burning questions. But one last question before we wrap this up. It's coming from Rodrigo Diaz, and he's asking if there are some studies that you know of that shed some light on the toxicity or higher release of toxic gases from electrical propelled vehicles or other vehicles.
Yes, well, I saw some of these studies, but, well, I also saw some studies that, well, there are some differences, of course, in the release of toxic gases, but, well, so far it's not like that we think that would lead to a very more significant number of casualties. But that may also be because we apply it mainly in our tunnels with a lot of escape doors and a lot of ventilation. So for now, for us, it doesn't seem the biggest issue to investigate. So for now we don't have any developments on that.
Given the scatter of all the assumptions you have, and that there's little perhaps significant influence, as you know now, as it stands now, on the tenability situations.
Yes, it's like we already have a lot of conservative assumptions, so I don't think it would be, well, it's in the same range of conservativity that we have this electrical car. So that's maybe maybe it depends on the level of detail that you consider a single fire, but on our model level, it's not significant for now.
Okay, thank you. Again, let me invite you, if you have other questions, you can drop them in the chat box. The chat box will remain open for, I think, some time. And you can also tune in perhaps later today. The recording of this webinar will be made available on our website, I think, John, if I say something which is not correct, you should correct me. And via our LinkedIn page of PFPNet. So I think that's all for this session. And let me thank you again, you Tineke, for your clear presentation. And see you perhaps later this afternoon. John, you want to say some final closing words, or?
Just a thank you to Tineke for that lovely presentation. Very well done. Thank you very much. And thank you all for joining with us. And we look forward to the next session this afternoon. And just a reminder for those that aren't members of PFPNet, please take a minute to have a look at pfpnet.com and you will find more information of our activities. We are an organization where everybody participates, so it's not just a talking shop as such. We do have many engaging activities that you could join in with, so I would encourage you to take a look to see what we do and hopefully join us. Thank you.
Okay, thank you.
Thank you all. Okay, bye-bye.
Bye.
Bye.